So the uniqueness of water. Water, of course, is amphiprotic. It can act as a base when you throw in an acid. It can act as an acid when you throw in a base. So various fun little questions associated with that, some of which you may see, some of which might be a teensy bit past what you might see, but it's a good idea to have seen them. So concentration of hydroxide ions in an acidic solution with a pH 4.47, where you say it's an acidic solution, it's not going to have any hydroxide ions. No, every aqueous solution has H+ ions and hydroxide ions. pH 4.47, so the log of H3O plus is minus 4.47. So the H3O plus concentration 10 to the minus 4.47, or 3.39 times 10 to the minus 5 molar. We know that at 25 degrees Celsius, the H3O plus times the OH minus equals Kw, so 1 times 10 to the minus 14. Plug that in and you could solve it. Alternatively, you could use the other relationship, which is that pH plus pOH equals 14. So if the pH is 4.47, the pOH is 9.53. Now do the same type of relationship. Log of OH minus is minus 9.53 therefore. So the OH minus, whichever way you do it, 2.95 times 10 to the minus 10 molar. You can either work it through to get the H3O plus, then the OH minus, or you can get the pOH from the pH and then get the OH minus that way. Concentration aqueous BaOH that has pH 11.5. Well, again, pH is H plus. You've got OH minus, but remember there's relationships between them. pH is 11.5, so I would say pOH is 14 minus that, which is 2.5. So minus the log of OH minus 2.5, or the OH minus is equal to 3.16 times 10 to the minus 3 molar. Okay. Now, of course, that's the OH minus. I didn't ask you for the OH minus. I asked you for the BaOH2. There's two OHs in each BaOH2. So thus the concentration of barium hydroxide is 3.16 times 10 to the minus 3 divided by 2, 1.58 times 10 to the minus 3 molar. Now this one is lovely. pH solution 1 times 10 to the minus 9 molar NaOH. Unthinking people would throw it in their calculator, get 9, subtract that from 14 and get 5. Then they might say, hang on, this is base. 5 is acidic, so maybe it should just be 9, right? Log of 1 times 10 to the minus 9. However, what they're not doing there is they're not thinking it through. So let's think about it in two ways. First of all, qualitatively. Well, it's a base, okay? But it's only a teeny little bit basic, 1 times 10 to the minus 9 molar. So therefore, it's only going to be a teeny little bit more than 7. So answer D. Quantitatively, where does that come from? Well, the OH minus is 1 times 10 to the minus 9 molar from this. But remember, water has OH minus and H3O plus, and at 25 degrees Celsius, that's 1 times 10 to the minus 7 of each of those. So there was already 1 times 10 to the minus 7 molar OH minus before you added anything. Ordinarily, it's so small, we ignore it. But when we're only adding a teeny little bit, we can't ignore it. So the OH minus is about 1.01 times 10 to the minus 7. Okay, so therefore the pOH is minus the log of that, which is 6.996. But of course, pH is 14 minus pOH, which is about 7.004. Either way you do it, pH should be a little bit more than 7 because you've added a teeny little bit of base. Now, I like this one. It's a little beyond some of the A-level thinking, but if you go back to some of our equilibrium discussions, you should be able to see it. Okay, given the Ka of HCN, 4.9 times 10 to the minus 9. So we can see HCN there, we can see its conjugate base there, Cn minus. But we also got this OH minus and water. Well, let's write out two different equilibria. HCN plus H2O goes Cn minus plus H3O plus. That's the Ka. We know that's 4.9 times 10 to the minus 9. And in any aqueous solution, you've got water, giving you OH minus and H3O plus. And that's just Kw, which is 1 times 10 to the minus 14. Now, if we combine these equilibria in such a way that we get this equilibrium, we can get the equilibrium constant for this one by combining appropriately the k values. Now, when I look at these, I see, well, there's HCN, which is where I want it. There's CN minus, which is where I want it. But I'd like an OH minus on the left, and I'd like an H2O on the right. And I'd like to get rid of this H3O plus and this H2O. Well, if we take this second equation here and we flip it, then we get OH minus plus H3O plus goes to 2H2O. Now, if I add those together, the water, H2O plus here, cancels out with one of the waters from the flip to number 2. The H3O pluses cancel out. So I add those two equations together, 1 plus the flipped 2, and I get the equation I want. Well, the way I do the k's then is for equation 1, I just use the value as given, 4.9 times 10 to the minus 10. But equation 2, I was given 1 times 10 to the minus 14, but then I flipped the equation, and when you flip an equation, you flip the k value. So it becomes 1 over 1 times 10 to the minus 14. And then when I add equations together, I multiply the k values. So do all that, and I get 4.9 times 10 to the 4. Okay. Conceptually, an extremely important question here. Make sure you're okay on all the little components to it. You might have to go back, look at some of the equilibrium chapter and some of the equilibrium extension material, even though it should make sense to you just from the very definition of equilibrium and equilibrium constant. At 37, Kc for this reaction, 4 times 10 to the minus 6. If Ka for HA at 37 is 8 times 10 to the minus 9, calculate Kw. Well, this one is again kind of fun one. Kw is Ka times Kb. Okay, well, here's our equation. A blah, blah, blah goes to HA, and we know that for A minus acting as a base, the Kb is equal to 4 times 10 to the minus 6. Okay, so therefore the Ka for HA, 8 times 10 to the minus 9, times the Kb for A minus, 4 times 10 to the minus 6, is going to be Kw, 3.2 times 10 to the minus 14. All you had to do is recognize that you got HA is the Ka value, here is the conjugate base of HA, A minus, here is A minus, acting as a base, so this is the Kb for A minus, Ka times Kb equals Kw. So the reaction vitamin C is shown, so not actually showing this as Bronsted-Lowry, but never mind. There is the C6H8O6, that's vitamin C, acting as an acid, so that's its conjugate base, and H+. And which would cause the equilibrium to shift to the right. So in others want it going over this way. Well, if I dissolve more vitamin C, that's adding a reactant. For any reaction, when you add a reactant, it drives the equilibrium to the right. So that looks pretty good for the right. Adding in NaC6H5O6. Well, this is the same as adding C6H8O6 minus. So we're effectively adding a product. Any reaction, when you add a product, is going to shift the reaction to the left. Lowering the pH, well, lowering the pH is adding H+. We're adding a product, so that shifts it to the left. And then finally, adding hydroxide. Well, if we add hydroxide, that will neutralize the H+. So that's like we're removing a product. And any equilibrium, when we remove a product, the equilibrium will go to the right. So therefore 1 and 4 send it to the right, 2 and 3 send it to the left.